Sorry about this confusion today. So today we're going to talk about lesson 5, which is molecular and ionic substances. So basically, this is telling how chemicals bond in nature and how they occur. So for week 4, the class range for the homework was 5 to 8, so that was pretty good. You guys did a great job on that. This week, there's 6 questions in a Google Forms quiz under the Classroom tab in Google Classroom. I'll give you written feedback and post your grades on Google Classroom. And if you have any questions during this lecture, please post them in the private chat. Please don't use the public chat. Just PM them to me. And if you have any questions or suggestions on how to do this course, please contact me at this email. Okay. So today we're going to be talking about 3 things: molecules, ions, and chemical equations. A review. So we're going to first talk about molecules. So a molecule is a group of atoms chemically bonded to attractive forces. That they're able to bond is because it's lower in energy when they bond together. And this is called molecular bonding, when they share electrons and bond. So when atoms bond in molecular bonding, they share 2 electrons. Each bond is equal to 2 electrons, and each atom donates 1 electron to each. So as you can see in here, this is 1 hydrogen atom with another hydrogen atom, and then they bond together and they both donate 1 electron. See, these 2 atoms both donate 1 electron here. Hydrogen bond. Can everyone please mute their microphone? Thank you. And then how you can represent a bond is you can represent it by a dashed line. So this is the same thing as H2. This shows how the molecules bond. So as you can see, each dashed line equals 2 electrons, which is the same as these 2 electrons right here. So this is a new symbol where each line is a bond. Sometimes you can see double bonds like this, and each of these lines are 2 electrons by themselves. So there's a total of 4 shared electrons between these 2. And there's also a triple bond where each bond is still 2 electrons, so they share 6 electrons. So you can have multiple different types of bonding. So there was a little confusion about molecular orbital last week. Molecular formulas last week. So I'll reiterate what that means. A molecular formula gives the exact number of different atoms in a molecule. So this is a molecular formula, CO2. That means for every carbon atom, there's exactly 2 hydrogen atoms. And this is how it occurs in this format. The carbon atom is in the center, and then it bonds with 4 electrons to each oxygen atom. Remember, each line represents 2 electrons. So if you have 2 lines, that's 4 electrons bonded between carbon and oxygen. And then there's 4 more electrons bonded between this carbon and this oxygen. So this is what CO2 does. So this is the molecular formula. CO2, this is the molecular formula, and it tells exact number. So now we're going to describe more about water. So H2O, as you guys all know, contain 2 hydrogen and 1 oxygen atom. And between each oxygen and hydrogen atom, they each donate 1 electron to form an OH bond. And the bond arrangement is OHO. So it must be in that order. As you can see in this picture, a hydrogen bonds to 1 oxygen and 1 other hydrogen. Note that the different other arrangements like OHH and HHO are both incorrect representations of water. So you can't mix up the order in the atoms. And this is why. So in a hydrogen atom, it only has one electron to donate, so it could only form at most one bond. But an oxygen atom, it can donate 1, 2, 3, 4, 5, 6. It can make up to 6 bonds with oxygen. So oxygen's going to be in the middle, and then the hydrogens are going to be at the ends, like this molecule. So they share electrons. So between this bond, there's 2 shared electrons here. With this bond, there's 2 shared electrons there. So that's how covalent bonds work. It's sharing of electrons. And each molecule in a bond gives 1 electron. So if hydrogen bonded with 1 oxygen, one of these would be shared, and then they'll form a bond. So that's how the bonds form. Let me clear that. So here's another compound that's pretty interesting. It's called hydrogen peroxide, and it's commonly used in like the cleaning of wounds. If you pour it over like a cut, as you can see up here, there's a bubbling, and all of these bubbles come out on the top. It actually undergoes this reaction. H2O2 yields H2O plus O2. And to balance that equation, you'll just do 2, 2. So chemists can decide that the bubbles are actually oxygen bubbles. So those bubbles are oxygen atoms coming out. And that's why it can kick out the germs. It bubbles everything out, so it bubbles the germs out. So that's why it's effective, hydrogen peroxide. And H2O2, in the chemical formula, there's 2 hydrogen atoms and 2 oxygen atoms. And the arrangement that the bonds form is HOOH. And the reasoning it has to occur in this way is like in the last slide, hydrogen only has 1 electron, so it can only form up to 1 bond. So a hydrogen must be at the very ends. Like in all of these 5 examples, they're incorrect representation because this hydrogen is forming 2 bonds, and we know hydrogen cannot have 2 bonds because it doesn't have 2 electrons. This hydrogen violates that rule. This hydrogen violates that rule. This hydrogen doesn't validate that rule, and these 2 both break that rule. So that's why it must be HOOH, like this way. So later on, I'm going to be asking questions like, I'm going to give you one of these diagrams, and I'm going to ask you, what is the molecular formula? So you're going to have to know it's going to be H2O2. Because there's 2 hydrogens and there's 2 oxygens. So it's H2O2. So that's the molecular formula if I give you like a structure like this. So now we'll move on. So there's a common mistake with H2O2 that I saw in the last lecture. A lot of people thought H2O2 is equivalent to HO, since after all, I said last lesson, it's a ratio thing. For every 2 hydrogen atoms, there's 2 oxygen atoms. So you might be tempted to think it reduces down to 1 to 1. But remember that in the beginning of today, I said a molecular formula tells the exact number of atoms bonded together. So this molecular formula says that there's exactly 2 hydrogen bonded to 2 oxygen. It's incorrect to say that there's 1 hydrogen bonded to 1 oxygen. That's not the whole molecule. So that's why it's H2O2 instead of H2HO, because the formula tells exactly what bonds together. Okay, let me erase that. So you might be wondering, how do you order the compound, the letters, the the elements in the system. So there's this system that chemists use called the Hill system, and it states that carbon atoms are always first if they're present. Then hydrogen atoms are next. The reason that carbon and hydrogen atoms are first is because they're very common. So in a lot of molecules, especially ones that pertain to life, they're the most common atoms that exist. And then everything else is alphabetically ordered. But be aware that there are many exceptions to this rule, but right now we could just follow that rule. So first are carbon, if present. If there's no carbon, then just don't include the C. Then it's the hydrogens. Then it's everything else alphabetically. Okay, here's an example problem. So remember, please PM this to me instead of typing it in the chat so other people don't see the answers. So what is the molecular formula for this compound? You don't have to put the numbers under the letters, you can either use an underscore or you could just put the numbers directly after the letters. You don't have to put them under. I saw a few misconceptions today. The first thing is you have to realize, is this one atom or is it two atoms?
So you do always.
Yes. Did someone have a question? I guess not. So as you remember, it's two letters because the second letter is always lowercase. So this is just one element. So we now know it's one element. There's two chlorines in one molecule, so we'll put a chlorine 2. But I know in the chat box, you really can't put that subscript there. So just do like Cl2 or Cl underscore 2 or anything else that you can think of. So yeah, most of you got that one correct. So good job. Here's a slightly harder one. This compound, so please type it in the private message me when you're done. You figured it out. So what's the molecular formula of this? Okay, a lot of people have been getting it correct. So there's actually two possible answers to it. I had a question that says, do we always put the element with the most molecules first? No. Remember the slide that I said that talked about the Hill system? You first do carbons, then hydrogens, then everything else alphabetically. So that's the major rule if that was true. So we first see how many different types of elements there are. There's 2 of them. There's 1 nitrogen, and then there's 3 hydrogens. So using the Hill system, we would actually write the answer as H3N. But chemists, sometimes there's many exceptions to the Hill system. So because it sounds better, most people write NH3. Both of them are correct. They both show the same thing, and anyone would understand that. So good job, everyone. The one thing that I would point out is I prefer you guys not to do lowercase letters like in H3, because remember, in any atomic element, the first letter is always capitalized. So try to use uppercase letters instead of lowercase letters. So I have one more example. So when you have the time, try to do this one. And this one does follow the normal Hill convention, by the way. So this one isn't an exception to the Hill rule. So a common mistake is that you don't put the carbon atoms first. I'm sorry if you guys didn't know what the carbon atom is. It's the letter C. I didn't explicitly state that earlier. So carbon atoms or letters that start with C, they always go first. Well, not letters that start with C, just the element carbon. So like chlorine does not go first, but carbons always go first. Okay, I see that everyone got it right now. So the answer is CH4O, because there's one carbon and that one always goes first, then hydrogens, because they're the second most common element or priority, and then oxygen. So that's how you do it. So for homework today, you're going to have 2 of these examples to do, which you look at a molecular formula and you solve the problem. I had a question that asked, should you always write it in alphabetical order? For example, C is before H and O. No, it doesn't always work. So let me try to come up with an example where it doesn't work. Okay, here's one. CH3B. So B is for boron, and that one doesn't clearly have it in alphabetical order, but carbons are always first, then hydrogens, then everything else in alphabetical order. So that's how it works. Oh wait, I wanted to mention one thing. Remember that these things are bonds, and each bond shows 2 electrons, and they each share the 2 electrons in the bond. So now that was molecular bonding or covalent bonding, whatever you like to prefer to call it. It's the same thing. Now we're going to talk about a different type of bonding, which is totally different. It's called ionic bonding. It forms ions. So an ion is an electrically charged particle caused by gaining or losing electrons. I know it's a little non-intuitive right now why an atom would gain or lose electrons, because the stable form is neutral and that one's the most stable. But the thing is, if there's 2 isolated atoms and one of them's a metal and one of them's a non-metal, since metals are good at losing electrons, the metal can donate the electron to a non-metal. And after this sodium atom donates electron, it forms an ion called Na+. This plus means it lost 1 electron. And then this chlorine would just take that electron, Cl-. And then because these are charged particles, they would actually attract each other and come really close, and it's even more stable than the neutral forms. So this ionic bonding is even more stable than a neutral sodium and a neutral chlorine atom. It's because the sodium gets a positive charge and the chlorine gets a negative charge. We'll talk about it on the future slides how we determine the charges. But right now, metals tend to lose electrons and nonmetals tend to gain electrons. That's the usual trend. Let me erase. So we're going to talk about something called cations and anions. So basically metal ions or elements on the left side of the periodic table. I'll show you a picture of a periodic table and I'll point out the metal ions on a future slide. But since they only have a few electrons in the outermost shell, they tend to easily lose electrons and become something called cations, which is positively charged particles. But then on the other side, nonmetal ions or elements on the right side usually tend to gain electrons and become something called anions, which is a negative charged particle. So we're going to go more in cations. So here is a molecule of, this is a sodium atom. As you can see, there's 3 shells. This is shell number 1, shell number 2, and shell number 3. So the first shell is full. It has only 2 electrons in the first shell. In the second shell, it has 1, 2, 3, 4, 5, 6, 7, 8. And in the third shell, it only has 1 electron. So there's a principle in chemistry called the full valence shell theory, which states that the most stable atoms have a full valence shell. So it's really easy for the sodium atom to lose this 1 electron in the outer shell, and then this shell would be empty. If this was a third shell, it'll be completely empty and it'll have a full valence shell. So if you lose 1 electron, sodium has 11 protons. Neutral sodium has 11 protons and 11 electrons. And remember, this negative sign over the E stands for that it has a negative charge. So when we lose that, we're going to have 11 protons and only 10 electrons. And we're going to have 1 more proton than electron. So that's why we're going to write it as Na+. This plus signifies that we have 1 more proton than electron. So if we have another element like magnesium and it loses 2 electrons, then we're going to have a 2+. And aluminum loses 3 electrons, so it's going to be a 3+. So we just do the pluses by how many electrons they lose. But sodium only loses 1 because there's only 1 electron in the outermost shell. And it wants to be stable and have a full shell. Anions are the complete opposite. They want to gain electrons. This is an example of chlorine atom. As you can see, the first shell, which has these 2 electrons right here, these 2, it's completely full. Then the next shell has these 8 electrons, and that's completely full as well. But in the outermost shell, there's 1, 2, 3, 4, 5, 6, 7. The outer shell can fit at most 8 in this case, so it's just 1 electron shy. So if there's like an atom that readily gives up electrons, like if there's a sodium atom that just gives up an electron, then sodium, after it loses its last electron, it's Na+, and it has a full valence shell. Valence means the outermost shell, if you were wondering. And then this chlorine atom would have a full outer shell as well. So that one's really stable. And then because of these opposite charges, there's a positive charge and a negative charge, they would undergo bonding to make NaCl. So that's how these ionic compounds bond. So the metal first donates its electrons, and the nonmetal, which is chlorine, receives it, and it forms a pretty stable bond. It's much stronger than the molecular bond we talked about earlier in the last section. So here's a good way to remember the differences between a cation and an anion. So if you're a cat lover, this is really easy analogy. So cats are good if you're a cat lover, and it's a positive, as you can see. So cations are positive charged, and anions or onions, which is pretty similar to anions, they make people cry, so they're bad. So you could think of them as a negative charge. So that's how, this is a cute little way where you can remember the difference between a cation versus an anion. So remember, cations lose electrons to form a valence shell, and then they become positive charged because they have more protons than electrons, and anions gain electrons from the outer, gain electrons, and it becomes negative charged. So we're going to look at a few more examples, and then we're going to do a few practice examples after we get through them. So this is group 1 cations. So remember when I did the periodic table lecture, group 1 means it's this group right here. So this same group shares similar properties because it has a similar number of valence electrons, or the electrons in the outermost shell. As you can see at this lithium atom, there's 1 electron in the outermost shell, and in this sodium atom, there's only 1 electron in the outermost shell. And that's true for every single element in this category. The only exception is hydrogen, because hydrogen is such a weird element. It doesn't really follow this trend. As you can see, it's a non-metal, and every other element in this row is a metal. So we can just treat hydrogen atoms like an exception. So group 1 elements always like to lose 1 electron and form a cation if they react with any non-metal. So in this chart, you can see that most elements are metals, but then the non-metals are right here. They're the blue ones, non-metals. So if any of these group 1 elements come into contact with any of these blue non-metals, likely these elements would lose electrons. And group 1 elements always lose 1 electron because they only have 1 outermost electron. So they're going to become charged. Like if this lithium atom loses 1 electron, it's going to be Li+. For sodium, it's going to be Na+. For this element, potassium right there, it's going to be K+. And that's going to happen for every single one of these down. Group 1s are always going to have a +1 charge. So group 2, so that's the group right over here. It's similar to group 1, but in this case, it has 1, 2 electrons in the outermost shell, and this magnesium also has 1, 2. So it can donate 2 electrons to be stable. So it'll rather donate 2 electrons because it's easier to donate 2 electrons to get a stable than gain 6 to become stable. So they'll always choose the easier path. And then once you lose these 2 electrons, you're going to have a +2 charge. So beryllium, once it loses those 2 electrons, it's going to be Be2+. This magnesium, it's going to be Mg2+. And remember, if it's a positive charge, it's going to be called cations. And now this is the negative charge, which is called anions. So it's this group right over here. Let me choose a good color. Group 17 is this group. So as you can see in fluorine, which is the top element F right here, there's 1, 2, 3, 4, 5, 6, 7. So that's really close to a valence shell of 8. So it would like to gain 1 electron. And if you gain 1 electron, you're going to have 9 protons and you're going to have 10 electrons. So that's going to give it a negative charge because this molecule is negative. Similarly, for chlorine, there's also going to be 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So it's going to lose that electron and be a negative charge. Chlorine minus. So remember, they only become anions if they interact with any metal. So you need to expose chlorine with some of these metals, and then it'll become an anion to participate in this ionic bonding. Okay, here's a general ionic trend to review everything we've gone over. Elements in this period, which is group 1, they like to lose 1 electron because they have 1 electron in the outermost shell. In this column, they like to lose 2 electrons because they have 2 electrons in the outermost shell. Easy way for remembering is count which row, how many elements are in this, how many rows are to the left. So all of these elements are the first column. So the first column always has 1 electron. So just remember that these all have 1 valence electrons. This column all has 2 valence electrons. So they're going to easily lose those 2. In columns over here, this column right here is called the noble gas. It's the most stable. They usually never react with any other element because they're so stable. But then these, it's 1 away from this column, so it'll usually be a -1 charge. This column is 2 away, so it's a -2. This column is 3 away, so it's a -3. So that's a good way to remember. You don't have to remember these because they're kind of the weird ones. But to the left of this, this is 1, so it's a +1 charge, +2, -3, -2, and -1. So now we're going to do a few practice problems to try to get you used to it. So type your answer in the chat when you have it. So would this element Na likely become a cation / or anion, and what would be the charge associated? So here's a tip. All of these elements are not going to be in this weird block. So first you're going to have to find where Na is, and then you're going to have to determine, is it a cation? And then what would the charge be? Cation or anion? And would it be a +1 charge, +2, -1, -2? So I'll give you guys some time to think and find it. And some of you might not remember what a cation versus anion is. Remember, cations, it's positive if you're a cat lover, and anions are like onions and they're always negative. So that should help you a little bit. I see a lot of people got it right so far. And then remember the charges. I'll do a more explanation about the charges. So in the valence electrons, or the outermost shell, this one would have 1 valence electron. These would have 2, 3, 4, 5, 6, 7, 8. Since all of them want 8 electrons, they're all going to react differently to see whether they would give up their electrons easily, or would they rather take more electrons. Like these, to become 8 or 0, it would easily just lose 1, so it'll become a +1. This one has 2 valence electrons. It's easier to lose 2 than gain 6, so it'll be a +2. This one, it'll be easier to lose 3 than gain 4, so plus. This column, it's equally, so it could be either a plus or a minus, depending on each atom. 5, it's easier to gain 3 than lose 5, so it will be -3. This one, -2, -1, and these just don't react at all because they're very stable. And for another hint, Na is right here. So would it be a cation or anion, and what charge would it be? So like the charge would be like +1, +2, +3, +4, -1, -2, or -3. So like everyone said, it is indeed a cation. And the charge is +1. So, and it's a cation. It will become a cation because it's easier to lose 1. So that was that. We have 4 more of these to do. So how about this one? With this element, which is a O, not a 0, O for oxygen, is this likely to become a cation or anion, and what charge would it likely possess? Okay, if you're having difficulty finding where oxygen is, it's right here. So the first question you should be asking yourself is how many electrons are in the outermost shell? So there's 1 for elements here. 1, there's 2, there's 3, 4, 5, 6. Seven and 8. So we know it's 6. So a lot of you said anion, and that's correct because it's easier to lose. It's easier to gain 2 electrons and get 8. So if you gain 2 electrons, remember it'll be a -2 charge since you have 2 more electrons than protons, since you're gaining electrons. So when this oxygen, it usually has 8 protons and 8 electrons. When you gain 2, this 8 becomes a 10, and then you'll have a -2 charge. So a lot of you got the thing correct about being an anion, but just make sure your charges are correct. It's -2 instead of +2. Oh, whoopsies. How about this one? N, which is for nitrogen. Is it likely to be a cation or anion? And what charge would it possess? If you guys are having a difficulty time finding the element, well, this gives you a good exercise. Nitrogen is right here. So the first thing you should be asking is how many electrons are in the outermost shell. And then after that, you need to determine which charge it should possess. So let me start. So in this row, this one would have 1 electron, 2, 3, 4, 5. Since we want 8 or 0, is it easier to lose 5 or gain 3? It's easier to gain 3. So you're going to have a -3 charge, and it's going to be an anion because it's easier to gain 3 than lose 5. So that's the correct answer for this one. It's another anion. -3. How about this? Mg. This one might be a little harder to find, but I'll just give you some time to look at. Okay, I'll give you a few more seconds, but I'll help you find it. It's right here. This element is called magnesium. So would this element likely become a cation or anion? And what charge is it most likely to be? Okay. Yep, we can do the same thing as we have been doing in the past and determining how many electrons there are. So there's 1 electron here, 2 here. Is it easier to lose 2 or gain 6? It's easier to lose 2, so it'll be a +2, and it will be a cation. So it's a cation +2. Okay, here's our last one for the day, Cl. This is the same element we saw earlier. This is the first exercise, I believe, where we had 2 Cl atoms together. But is it likely to be a cation or anion? And what would the charge? Remember, cations are always positive. So if you answer a cation, you should always put a positive charge. Anions are always negative. Think onions. So they're always negative. Okay. I'll give you a hint. Chlorine is right here. So would it be a cation or anion? And what would the charge be? Okay, let's work through it. This is 1. There's 2. This is 3, 4, 5, 6, 7, 8. Since they want 8 electrons in the outermost shell, it's going to have a -1 since it's going to gain 1 electron. Because you want to have a full shell, so it's going to be -1, and it's going to be an anion. So good job. It's an anion, and it's going to be a -1 charge. Remember, these elements at the very end have a 0 charge because they're very stable. So these would have a -1. The oxygen and sulfur would have a -2, -3, and so forth. So today, now we learned the 2 types of bonding. I'll go over a quick review. There's 2 types. One of them is called molecular bonding. That's where they share electrons, and it's usually between 2 nonmetals that share electrons. And the second type, which we did ionic, which we just talked about cations, anions, and the charge, that's between 1 metal and 1 nonmetal. Let me go back to the metal. So an ionic is always 1 metal with 1 nonmetal. So we have 1 red, so 1 of these, and then we have 1 of the blue. So that's ionic. But covalent or molecular, the first thing we talked about, it's always 2 plus of the blues. So only nonmetals can participate in covalent bonding. But ionic bonding, it's always one metal, one nonmetal. So now we're going to review the chemical equations. So this is the chemical equation I shared last week. So the first one, it's 2Li. The Li stands for lithium, and that's just a metal. But then H2O, we just discussed that earlier. H is a nonmetal, O is a nonmetal, oxygen. So this one is going to do molecular. So it's going to participate in the first sharing of electrons, where they each share one electron to that bond. This is a weird one. It's actually, this Li is a metal, and this OH group functions as a nonmetal group. So this one is going to be the ionic. So the lithium is going to transfer that electron to the OH group, and it's going to be a traction of positive charges. And H2, it's just nonmetals, so this one is molecular as well. So now we kind of understand the types of bonding. We can understand these chemical reactions better. So like I said last time, the reactants are the starting materials. Some of you missed that on the homework. So the starting materials are anything before the arrow. So lithium metal and water, both of them are reactants. The products are things at the very end. So lithium hydroxide, which is LiOH, and hydrogen gas, which is H2. Those are what you call products. They're the things that you form. Coefficients tell you the proportion. I think this confused a lot of people. So this coefficient, you can just say it's a ratio 2 to 2 to 2 to 1. And you could just drop down the coefficients. So we always know it's going to be react in this proportion. So like if I say that there's 5 hydrogens, we're just going to do math, and we multiply this by 5, so we multiply everything by 5. So we have 10 to 10 to 10. So that's how we use these coefficients. Not these subscripts. The subscripts tell about each individual molecule, but these coefficients, which are outside, they're always before the compound. That gives us the ratio we need. So that's basically what I said. And now we're going to review this problem. We didn't get a chance to finish it last week, so I want to review it. And this is the last thing we'll do today. So the equation N2 plus 3H2 yields 2NH3 is a general process chemists use to synthesize ammonia, which is a useful product in household cleaning and pesticides. So in the chat, type in the reactants of this reaction. So what are the reactants? You don't have to type in the coefficients, but you can if you want to. We might go a little over today since we were a little late to start. Okay, so the first one is going to be N2. So N2 is a reactant, and H2, because anything before this arrow is a reactant. So I saw one mistake where someone did N and H. That's not correct because the N2 is needed. This 2 is needed for the molecular formula because it's 2 nitrogens bounded together. You can ignore the coefficients, which are the numbers out in front, but you can't ignore the subscripts. I know it might be a little hard to type, so just type capital N and then just type a 2 after it for N2. So what are the products of this reaction? So please type that in the chat when you've got it. So when there's something like NH3, that's one compound. So it's not N and then H3, it's just one thing, NH3. Similar like the N2 and H2 thing. Okay, so we're gonna do a few ratios. So if 2 moles of NH3 are formed, how many moles of N2 react? I had a question that says, why is N ahead of H? This is one of the exceptions to the Hill's rule that I talked about earlier. You can, if you say H3N, that's perfectly acceptable as well. But the general convention chemists use for ammonia is NH3. That's a great question. And a lot of people got it right. It's 1. We can just use a chemical. It's 1 to 3 to 2. So if there's 2 moles here, there's 1 mole in 2. Okay, let's get the H2. Let's go down to this problem. If 3 moles of N2 react, how many moles of H2 are needed? So we could just have a diversity of problems. Okay. Everyone who answered got the right answer. It's a 1 to 3 ratio. So if 3 moles of N2 react, there's going to be 9 moles of H2 that are needed. So great job, guys. So the lesson recap today, we covered molecules, ions, and chemical equations. And lessons 7 and 8, I've decided are going to be review lessons. We're going to cover the same things we've covered in 1 to 6, but we're just going to focus on different problems and different applications and have a good review of those concepts. So for this week, there's going to be 6 homework questions. 2 of them are about general concepts like what's molecular bonding and what's ionic bonding. And 2 of them, you're going to have a compound and you're going to have to give the molecular formula. And the last 2 are, it's going to ask if it's an anion or cation and what's going to be the charge. So it's going to be really similar to the ones we did today, and you're going to have to find the elements on the periodic table. If you have any questions or suggestions, please contact me at this email, and I'll post the lecture notes later today, as well as homework. Bye, guys. I hope you have a great rest of the week.